Good morning. Good morning. Can you hear me? Yeah? Very good. Very good. This talk is, I guess, in some ways, an introduction to Node.Js for Java developers, but also kind of a personal history. So I did Java for at least 10 years, mostly in the end on the JBoss platform. And then about 5 or 6 years ago, decided to take a look and experiment with this crazy little project called Node.js. And it kind of took off, and with 1 or 2 other people, I decided to set up a consulting company. I had done a whole bunch of startups, some more successful than others, but I decided to kind of grow up and become a consultant instead. And I had to learn how to move from Java to Node.js. And of course, there were absolutely no guidelines. Node was really, really new, very fragile and unstable platform. And we made every single mistake. We built applications that didn't scale. We built spaghetti code. We worked with large enterprise teams that ended up as death march projects because we didn't build code that could handle technical debt. So this talk is not about the sort of fine-grained details of how you manage callbacks and that sort of stuff. There's 1,000 blog posts. This is at a slightly higher level. This is about how do you manage the architecture of Node.js. And if you've been building Java in the enterprise, you're used to building large systems. Large not only in terms of the user base, but large in terms of the code base and the number of developers. And there's a whole set of best practices and design patterns and all that sort of stuff that let you manage technical complexity and keep technical debt under control. And that stuff is not directly transferable to Node.js. Yes, some of the best practices, like unit testing, of course, transfer pretty directly. But other types of structure, a lot of the design patterns in object-oriented programming that you're used to don't transfer because the platform and the language is different. So I'd like to get a little bit philosophical for a minute. This is the flight deck of the Space Shuttle Atlantis. This picture was taken on mission STS-101. The software that controls this vehicle or controlled this vehicle is some of the most perfect software ever written. It's about 420,000 lines of code, and the cost per line of code is about $1,000. They produced about 1 bug every 3 months. So it was pretty much as perfect as it gets. But you can see how expensive it was to produce. And I think there is an underlying assumption in a lot of the enterprise work that we do, an implicit, unspoken expectation that this is the level of quality that we're trying to achieve. We're trying to write perfect software. And sometimes it's politically impossible to say, hold on a minute, we need to cut our cloth to suit our measure. And sometimes, especially when we're in the early days of our careers, we aspire to write perfect software like this. And the problem is, this is far too expensive. Think about all of the custom integrations that had to happen. Think about all of the interdependencies in that code base. You can't build code quickly enough in the enterprise if you're trying to build code like this. You have to find alternative approaches, engineering approaches, and project management approaches. And one of the simplest ways is to use software components, to have code that is reusable and code that you can fit together, that you can compose together to build bigger systems. This is kind of epitomized by a slightly different vehicle. So this is the Gossamer Albatross, and this was the first human-powered aircraft to fly across the English Channel. It was built to win a kind of an X Prize. So in 1959, an industrialist called Henry Kramer offered £100,000 sterling, which was worth a lot more last week than it is this week. So I was on holiday in the UK last Friday. So when I went on holiday, I was in the EU, but I was really glad to come home to Ireland and go back to the EU. Yeah, those crazy English guys. Hey, look, it's never going to happen. In Ireland, we had a referendum, we said no, and then they just did another one, and we said yes. So it's kind of cool. So the guy who won this prize was a guy called Paul McCready. He won it 20 years after it was first posted. So the prize was set up in 1959, and he won it in 1979. And what happened was, for most of that time, people who were trying to win this prize would spend a year designing an airplane. They'd get into the airplane, pedal furiously. The thing would fall apart, or 500 yards later, they would collapse with exhaustion. And then they'd go back to the drawing board, and this is in the 60s and 70s, so a literal drawing board. And they'd spend another year designing an airplane, and they'd do it again, and they'd fail again. And the guy who won the prize, Paul McCready, realized that the issue wasn't flying across the English Channel. The issue was figuring out how to iterate the design of the airplane very quickly. How can you build 3 of these in a day to work out all the bugs? And he realized you needed a component system. You needed a system of Kevlar and aluminum piping and wires that you could compose together in different configurations. And it only took him a year. So 20 years versus 1 year. It wasn't perfect. It wasn't as perfect as the space shuttle, but it worked. This is the model that allows us to build enterprise software within the time and quality constraints of the real world. This is a different mental stance, a stance based on saying, how do we compose large-scale software? Not large scale in the sense of user volume, but large scale in the sense of large teams and large code bases with components. What is the component model? If you don't think about your component model when you build Node.Js, it's JavaScript, you end up with this. This is a yak in the Himalayas. So eventually your code base becomes so complicated that to change anything, you eventually end up having to climb the Himalayas and shave this yak. Because your code has become so interdependent. We did this a lot. So you hear a lot about the mean stack, right? So Mongo and Express and Angular and Node. But if you just start building mean stack applications and you apply the principles that you've learned in traditional object-oriented coding, MVC patterns, that sort of stuff, you try to build that in JavaScript as a single monolithic code base, you end up with this. In the enterprise, if something is possible in a programming language, somebody will do it. That's why Java controls things and C# controls things so much, and you have different access levels and that sort of stuff. And even then, people do crazy stuff. Well, imagine JavaScript, which lets you do pretty much anything, invent your own object, inheritance models, all that sort of stuff. People are going to do crazy stuff, and you end up with highly complex code bases. So there is this myth that Node gives you high productivity. What's actually happening, and this is what we've seen, is that Node is adopted by forward-thinking teams who tend to be better developers. And they do really, really well, and they're really fast. And then Node spreads out or gets wider adoption in a company. And then you end up with this. Because the language and the platform is so free that there aren't, in fact, sufficient constraints to control technical debt. So it comes back to the component model. And you want something like this, something like Lego, where things can fit together, and you know they're going to fit together. And if I add a red brick to the top of that house, the yellow brick at the bottom doesn't have to change. There's no complex web of dependencies. And yes, it's a cliche to use Lego as an example of a component model. But at the same time, it really does capture the essence of what software components are meant to do. Different teams can work on different bricks, not interfere with one another. How many of you guys are using Node? Okay, so there's a lot of people here, I guess, who are looking at it and trying to understand what the implications are of moving to Node. And again, I have to kind of emphasize, it is not about the fact that it's asynchronous and event-driven and lightweight. Those are reasons to use Node, technical reasons. The issue here is, once you move away from the toy applications, how do you build the big ones where you have large teams? The problem with Node is JavaScript. It's a strength in the sense that JavaScript is ubiquitous, and it has some nice properties, but it's also a massive weakness. The language is too free. The problem is you can't just analyze this problem from the perspective of the language. You can't just say, well, JavaScript isn't good enough for the enterprise, so we can't use Node. The problem is this chart. You may not have the choice soon enough. Adoption of Node in the open source community and adoption of Node in the enterprise community has been phenomenal. It's probably the fastest growth curve of any major language platform. So the number of modules is growing exponentially and very quickly exceeded most of the other platforms. Again, I would be the first to say that you can take 75% of those modules and question their quality. But it's not so much the fact that there is a significant quality issue. The mere fact of that exponential growth curve is telling you that irrespective of the technical foundation of the platform, and irrespective of whatever benefits it brings, there's a fashion movement going on here. Enterprises are moving to Node. And for a lot of teams, and a lot of teams that we work with, they don't have a choice. Somebody higher up the chain has decided, oh, I've heard that Node lets you develop faster, therefore you guys are using Node. And they're not going to listen to arguments about, well, actually, JavaScript as a language doesn't scale in terms of code volume. So you have to figure out how to address that issue. If we take a look at what we see in terms of enterprise projects, yes?
I asked a question on Monday to the guys in Keynote. We are with launch, and my question still remains: does Node.Js actually throw out Java, or is it part should be like in co-inherent or live together with Java?
Okay, so the question is, does Node.js completely replace Java, or does it live together? Funnily enough, this slide kind of addresses that question. So this is what we see. This is the three types of projects we see predominantly in the enterprise. One is where there is an existing Java system. It's not going away. There's been 10 years of work. The system is stable. It works in production. But for the most part, people are looking at doing extensions to the system and new development using Node. So there's a parallel track. There's a move to a polyglot approach where there's multiple languages in the system. And that's made easier by things like containers. Another type of project that we see is one where Node is replacing Java. So a migration style project where a deliberate decision has been made to completely move the platform away from Java towards Node. And typically what you see there is people adopting things like the strangler pattern, where they put a proxy in front of the entire old Java application and slowly start proxying requests to the new Node stuff. I would say that these three types of projects, moving from left to right, most of them are extension projects, followed by migration, and then greenfield full stack projects. So this is where somebody is building an entirely new system, and they decide they want to have full stack JavaScript. So that's JavaScript on the client, JavaScript for the mobile apps. So Mio can tell you a little bit about JavaScript on mobile apps as well. And obviously Node on the back end. So you have JavaScript everywhere. For the most part, most people don't have the freedom to have a fully greenfield implementation. There are always other components. So, for example, you might be using an SSO system, Keycloak, for example, and you might have to integrate with it. So it's not the case that you can just completely throw out Java. Java has a massive install base. You always have to work with it. Let's take a closer look at JavaScript. And I've identified JavaScript as the sort of key issue with Node, really. The approach that Node takes, the asynchronous event-driven model, you can see that in a lot of other platforms as well, and it's a really good model for scaling. It has one significant gotcha, which is if you're not careful, you can burn the CPU. So if you do CPU-intensive stuff, you end up blocking anyway. That's just a feature of that approach. But turning to JavaScript, the pros, as we would see them, are it is a terse and expressive language. An empirical fact is it takes fewer lines of code to get the same stuff done. That's a good thing because the number of bugs is sort of directly, linearly proportional to the number of lines of code. And there's a number of studies that show that pretty much. So the fewer lines of code you have, the fewer bugs you have. JavaScript is end-to-end, so you have the same language on the client side and the server side, potentially in the database, which is nice because every developer potentially can work on every part of the system. And it's also a compilation target. So if you don't like the language, you can use TypeScript or CoffeeScript or something like that and have a tool chain that compiles a better language into JavaScript, which is your target. The cons, and this is where the danger arises. JavaScript, the language, is deeply flawed. It was designed in 2 weeks in 1995, I think. So here you have a large-scale enterprise platform, a language where the first thing you learn is this half of the language, you don't use it because crazy stuff happens. So now you have to somehow enforce in your development teams not using this whole set of features, as opposed to a language like Java, which is designed from the ground up to stop you doing stupid stuff. It's not type safe. So it has a completely laissez-faire attitude to types, which is great for initial development because it goes really, really fast. But then if you want to do refactoring, it doesn't work. So one of the key things you learn about JavaScript pretty quickly, especially when you're building big systems, is an IDE is much less beneficial. It just doesn't help you as much. The IDE can't tell as much about the code. Auto-completion isn't as useful. And it can't do powerful refactoring. So if you have a very large code base, you have a big problem. You can't easily change things. You're very dependent on having high unit test coverage. And then it's a compilation target. And that's also a con, because you have these super complex tool chains where the whole idea of JavaScript was it was supposed to just work straight away, and it was supposed to be lightweight, and now you have a whole set of compilations that you have to do, and different versions of different languages. If you've ever tried to follow any of the React tutorials on the web, right, you have to install Babel, you have to do all sorts of crazy stuff to get React to work. So the language itself is an issue. And without fail, the effect this has is that large code bases collapse under technical debt. And we've seen this time and time again. Our customers come in, ask us a lot of times to help us with existing projects that have gone wrong like this. We've done this ourselves. The only real answer with JavaScript, right, is because these large enterprise teams struggle, because traditional design patterns, object-oriented design patterns, and agile techniques don't work as well. The only real answer is to reduce the size of the code base. If you have fewer lines of code, if you can eyeball the code, if your component is just a couple of hundred lines of code, you can kind of work around most of these problems. If your code base is tens of thousands of lines of code, then you have a problem. So at the start, I talked about component models, and it's therefore relevant to ask, well, what is the component model in Node that helps you get around these problems? I want to have components that are a couple of hundred lines of code that I can compose together. And this is the way that I'm going to manage complexity. I'm going to have components, and I'm going to ask, what are the design patterns for these components? So I'm going to set aside my object-oriented design patterns because the language doesn't give me much of that. And I'm going to say, at a slightly higher level, I have components that deliver features. How do I put them together? The first place you look is NPM, the Node Package Manager. So this is the system that has 150,000 open source modules, and you can use it internally in the enterprise. You can have your own private repositories, all that sort of stuff. The Node module system is pretty cool. So it encourages small and inspectable code. In fact, the paradigm for Node modules is you export a single function, a single constructor function that builds whatever the feature is of the module. And typically, if you look on NPM, if you look at the open source modules, you'll find that on average, they are a couple of hundred lines of code. They're inspectable in the sense that if something is broken, it's not a black box. You open up the code and you just read the code, which is fantastic. That's a great aid to productivity. And if something is broken, fork it and make a change, and then pester somebody for a PR. And it's versioning done right. So this is one of the coolest things about Node. And I would honestly ascribe 50% of the success of Node to the versioning model that NPM uses. So instead of having conflicts, right? So everybody here has probably had class loader conflicts at one time or another. The versioning model that Node uses is to, if you have a dependency, it explicitly imports the exact version that you need, and so on down in a tree. So if I have version 1 over here, I can have version 2 over there, and the dependent modules only see the versions that they use. And you never have conflicts, which is it's absolutely fantastic. You don't have to worry about that sort of thing. There's a huge choice of modules, so you can pretty much find a module that does whatever you need. But on the con side, the quality issue is a major, major problem. You have lots and lots of modules that were written by junior developers that were abandoned. You have to use a kind of rules of thumb. How many stars does it have in GitHub? When was the last commit? How active is the user community? It's kind of hard to tell. So if you want to do a HTTP request, do you use request? Do you use needle? Do you use rec? Right? So, and there's like 10 other ones. It's really hard to tell which is the best one. And request, which is the most popular HTTP request module, has loads of features, but it's slow. So did you know that? Who's going to tell you that? Rec is super fast and has 100% test coverage and is written by the guys at Walmart. So it has a completely different enterprise perspective. But did you know that? How do you know these facts? And how do you know them for 150,000 modules? And what is the provenance of the IP? Is all this stuff properly open sourced and using the right modules? And is there a GPL module stuck in there somewhere? There's a whole bunch of issues like that. One of the other problems is they're not composable modules. What I mean by that is you can't take a module, plug it together with another module, and then plug it together again. So think of Unix pipes, where I have small command line programs, and I can pipe them together because it's just a stream of text. And I can pipe a whole load of them together to do stuff. You can't do that with modules because the interfaces are too complicated. There's still function calls with signatures that you have to know and different signatures and that sort of stuff. So we don't really get composability. You sort of have to do it yourself every time. And the huge choice is a con because you don't know which ones are good. So this, as a component model for enterprise development, is too low level, and it doesn't really solve the problem. And if you're using Node modules as your building block, you are still going to end up with technical debt. Which ultimately leads to the conclusion, and this is the place that we came to from hard experience, from getting it wrong and ending up in a bad place. If you're going to do Node in the enterprise, you better be doing microservices. So in the Java world, this idea, the idea of microservices, whatever you think they are, is an architectural choice. Our position, strongly held, is that in the Node world, microservices are not an architectural choice. They are the way that you manage complexity, because you need to have components that are just a couple of hundred lines of code. And you need to have components that you can compose together. I've been using this word, software components, sort of freely. What do I actually mean when I get down to what is the nitty-gritty here? This is a picture of, it's from a book written in 1868 called 507 Mechanical Movements. It's on the web, it's been open sourced. Somebody's actually animated all these things, it's really cool. These are all mechanical components. And what are their properties? Is it that they're reusable? Is it that they're extensible? Do they have well-defined interface contracts? What is the essence of a software component? What makes it something that makes you build software faster? And the answer is none of those things. The answer is composability. I can be guaranteed to put the components together. So I can have a base component that I can enhance by composing it together with other components. And when you think of Unix pipes, when you think of those command line programs, you're composing them together to create a more complex program. This is the reason people love functional programming, because the functions are composable. Right? And sometimes you have to do fancy stuff like monads and all that sort of stuff to get it to work, but still, one of the key benefits of functional programming is that you compose functions together and you get a big piece of software out of small pieces that fit together nicely. Okay, so let's kind of step back just a little bit and think about this in terms of what does this mean for microservices? So this is a software diagram. It's a box with arrows. And so this means whatever, it means whatever you want it to mean. In this context, it means two microservices talking to one another over a HTTP call, right? So B exposes a REST interface, and A is the client. So this is the sort of classical understanding of what a microservice is. B is doing one thing and doing it well. It's a couple of hundred lines of JavaScript. It exposes some sort of REST interface. Maybe it's looking after user logins. Who knows? And A is another microservice, which is making a call to it and expecting a response. So this is the concrete implementation. This is how you build microservices in some senses, right? There are other ways to get them to communicate. Where is the component model here? Because if you think about it, this diagram could also be a diagram of objects making a method call, or Corba, or something like that. The problem is that when A calls B, there's a coupling there. A has to know about B. A knows about the identity of B. And that sort of breaks the component model, because it's very hard to compose components together when A has to know about B. It has to know about what B does and what its method signatures are and all that sort of stuff. There's too much coupling. It's very hard to replace B with some other system or wrap it in things that do throttling or caching or something like that. It's like the Lego bricks all have different sizes. For the Lego bricks to have the same size, we want a world that looks like this, which is A sends out a message saying, I want you to do something. And sometime later, somehow, B receives the message. And A doesn't know that B exists. It doesn't know where it lives on the network. It doesn't know that B is just one microservice. It doesn't know anything. So the contract between the services is just, I send out a message and somebody responds. And now you have this decoupling. But how do you go from a couple of hundred lines of a Node web server to this model? Because this is the model that lets you build large code bases, where you have components that are properly decoupled. And over time, in trying to achieve this, we've kind of uncovered two important principles. One of them is pattern matching, and the other is transport independence. So pattern matching is what lets you send a message, and it gets to the right place. It's a way to route messages from A to B without A knowing who B is. And transport independence is the idea that it doesn't have to be HTTP, because HTTP is synchronous, right? You might want to do asynchronous communication over a message bus or something like that. So it shouldn't matter how you do the communication. If your microservice is actually constructing the URL of a request inside the microservice code and making that request and dealing with the data, you're doing it wrong because you've created an implicit coupling. You've dictated that it's HTTP. You need to know the location of the endpoints. This is getting away from a component model. So what patterns does this leave you with? And again, what we're trying to look for is, okay, here's my OO patterns, like visitor and all that sort of stuff. What patterns can I have in this microservice component world? Well, here's the most basic idea. So B does some sort of functionality. It responds to messages that equate to the heart suit, let's say. And A sends out a message which is more specific. It's the king of hearts. So my system has to route the king of hearts to B because B is the microservice that deals with hearts. So if you think about user logins, B deals with user logins, and A says, I want to do a login for this type of user. The type of user might be an employee or a contractor or a guest or whatever. It doesn't matter. B always deals with logins, whoever they are. This is where the pattern matching comes in. B matches a more general version of the message. The pattern is a heart suit, and the specific message is king of hearts. So I've preserved the decoupling. If B specifically said king of hearts, it's more tightly coupled. This lets me do interesting things. For example, I can scale up because I can just add more Bs. And all I have to do is round robin between them. Now, the implementation of that round robining, does it go through an agent on each machine? Is there an Nginx load balancer? Whatever, is not relevant. We're talking about design patterns here. It's possible. This could be workers on a message bus. It's thinking about this idea. I can have multiple Bs, and I could have multiple versions of B. So let's say I have 10 instances of B running, and I want to update B. Well, I just change one of them to be the new version, and now 10% of my traffic or 10% of my load is going through a new version, and I can measure that to make sure that's OK. Just with this model, just with this pattern, I suddenly have the ability to do partial deployments and validate things in production without having to write any code or have any tooling or instrumentation to do it for me. I get it for free, essentially. It's just part of my deployment model. I can also have multiple microservices listening to the same thing. So when a user logs in, maybe I also need to do some sort of auditing, or maybe I need to check to see have they still paid their subscription or whatever. I can have different microservices listening to the same message. So this is a pub-subscribe model. And moving from the original model to a pub-subscribe model is no different than just adding more microservices. So this is a type of pattern that you get putting these microservices as components together. And you can see how I can have different teams of developers working on B and C, and they won't collide because they're not sharing any code. There's no dependency there. If A suddenly starts admitting the queen of hearts, it's still going to work. OK, maybe B is going to see fields that it doesn't understand, but it can just ignore them. It also lets you have an iterative approach to design. So with this model, typically the way a project works is that you start off with very, very general implementations, a general user login microservice. And then in each iteration, you specialize. So I needed to handle employees and contractors and guests. Well, in the old world, I would have designed a data structure and an object graph and all that sort of stuff to handle the structure. I would have looked for the nouns in the world and tried to model them. With this approach, I just say, OK, users log in. Week 1, I just have users log in. I don't care what type of user they are. And then in week 2, I can assign a developer, write the microservice that logs in contractors to my HR system. And I add that as a new microservice, and I don't touch the old one, so I'm not building technical debt because I'm not modifying anything, I'm just adding. And in this case, if I send out an ace of hearts, it goes to that specific implementation, and everything else goes to the old B. So this is another pattern that you can use. Start with the general and move to the specific by just adding new microservices. Or I can do composition. So this is kind of where we've been leading up to. How do you actually do composition? So if B is a user login, I might want to have caching, I might want to have permission control, something like that. I can inject new microservices in between the message flows. So in this case, C is now listening for hearts, and it generates heart prime, and B only responds to heart prime now. So maybe C is doing caching, or throttling, or adding a new feature, or something like that. So this is analogous to those Unix pipes or functional programming. I'm intercepting the message flows, messing about with them, modifying them. Now I have component composition. So to go back to the basic idea of this talk, you can't apply traditional object-oriented design patterns to building Node applications. You have to take a different approach. What we found is that you're forced into an object-oriented, you're forced into applying a microservice approach instead of an object-oriented one. You have to do microservices in the right way. If they're just small web servers, you get high coupling and you don't get composition. So you have to think about microservices as components that communicate via messages. It's interesting if you read some of the papers that Alan Kay has written about the design of functional languages. Some of the language written in the 60s and 70s is incredibly prescient because it actually talks about independent processes communicating via messages, which is a great way to have components. There is one little snag which I'd also like to talk about. We can't ignore this problem of service discovery because at the end of the day, let's say I am using HTTP. A still has to talk to B. At some point, somebody has to make a HTTP call. I can't ignore the real world. Somehow, A has to find the location of B. Now, I can wrap it in a library to hide it from the developer, but I still have to have some mechanism. Perhaps I'm hard coding it in a configuration file, or I'm using intelligent load balancing. So Netflix Ribbon, for example. Or perhaps I have a service registry. I'm using HashiCorp's console to look up the location of a service. DNS is a popular approach. Or a message bus, which gives you a lot of decoupling. We've used all of these techniques. They do work. But all of them still have some concept of identity. Right, the configuration file still has the IP address and port. If you're using DNS, well, you still have the host name. Even a message bus, the topic name is still a weak form of identity, so you still have this coupling. Remember, this is the world that we want to be in, where you send messages out of the universe and you don't know who gets them. Services should have zero knowledge of other services. And ultimately, we have to expect the underlying infrastructure to make this happen. So an interesting approach that we've started using in the last 6 months, which really enables this component model, is to use peer-to-peer service discovery. And the way this works is each service has a local view of the entire world. So each service knows where every other service is. And when it wants to make a call or emit a message, it locally knows where to go. Of course, this is hidden from the developer. So how do you make this work? Well, you use this thing. Right? Scalable, weakly consistent, infection-style process group membership protocol. As part of a family of algorithms that have arisen in the last year that let you do this peer-to-peer service discovery. So HashiCorp Surf, which is a on-machine agent, uses this approach. And it does work at scale. It's used by Uber. And we've used it very successfully. And it really makes the component model very fluid and efficient. It's a relatively complex algorithm, but the basic idea is that instead of pinging the whole network, you ping a small random selection. And those pings also contain new information about the network. So for example, the red service is pinging a small selection. And the fact that the pink service has joined, that message, that information piggybacks. So you can imagine all of these services pinging each other. An interesting side effect is that you don't have to wait 30 seconds. If a service dies, you don't have to wait for a 30-second timeout anymore because you have a really good sample, right? So 10% of the services might notice that a particular service is down because in that particular checking cycle, they happen to notice. So you can very quickly kill services that are dead. You end up with a model like this. In practice, A talks to B because you have this mesh network underneath. You have a library that can do the resolution. And this is a really, really powerful model because it means you have a zero configuration system. So one of the things that we've done is put together an example system in Node. So this is a Twitter clone. It uses 14 microservices. You can go to this GitHub repo and npm install and should run pretty much out of the box. And the README kind of takes you through the setup. And if you run into problems, post a GitHub issue, all that sort of thing. But it shows you how to build a scalable enterprise application. It shows you how you would decompose the different functionalities. And in particular, this application is not meant to be a toy application, right? So this is not an MVC model. It's a model that, in principle, scales to millions of users. So it uses a fan-out instead of just a simplistic data access model. It also shows you things like having a database per service, that type of stuff. And this approach is one that lets you build large applications in Node. Obviously, I can't show you code for my customers, so this is kind of distilling the approaches that we take. This doesn't deal with deployment and containers and all that sort of stuff, which is slightly out of scope for this talk. But to make this work in production, you do have to use containers. How am I doing for time? 50 minutes. OK, so I'm just going to do a quick run through of the application, just so you can kind of get an idea of how it fits together. It's a very, very simple Twitter clone. You don't have to log in. If you just type in localhost/foo, you are user foo. So if I'm user foo and I post a tweet, it comes up in my timeline. I can show I have a page, my home page, which shows me the tweets that I've posted. I can also search. So here I'm user bar, and I'm searching for a tweet that user foo has tweeted. And if I click follow, then I'm following user foo. So if I go to bar's homepage, I'll see the tweets for foo. And if bar starts posting, they'll see their own tweets. But foo won't, because foo doesn't follow bar. And bar, of course, sees everything. So it's an incredibly simple model of Twitter, but at the same time, handles things like fan-out. So if you have 1 million followers, it's still going to work. In practical terms, when I did a search for those tweets, there was a message going between services. So I had a search service that delivered that search page, and I have an index service that actually does the indexing of the tweets. And the search service emits this message, this JSON document, but it could be XML. JSON is easier in JavaScript. And the contents of the message are search query blue. Search query is the pattern that I'm looking for. So if I see a JSON document flying around the network that has search equal to query, that pattern is the pattern that I care about. And the indexing service says to the world, send me all messages that have search equal to query. And I know how to deal with them. And the other microservices ignore those messages. This lets you define the system in terms of messages. So one of the things that we often do is determine the requirements. Those requirements boil down to things that happen in the system. They can be encoded as messages. And when you have this list of messages, only then can you group them into services. So when you're building a microservice system in Node, you don't start by saying, what are the services? It's very hard to know. Start by asking, what happens in the system? What are the activities? What messages do I need? And then what's the most sensible grouping of these messages? So in this Twitter clone, you can see I need things like, I need to be able to do a search. I need to be able to insert things into the search index. I need to be able to post an entry. And when I do post an entry, I need to be able to emit asynchronously a message that says, I've posted an entry, so that the indexing service and the timeline service can say, hey, there's a new entry. I need to store it. So that's a sort of analogous to a CQRS pattern, right? So I don't know if you've heard of command query segregation, responsibility segregation. It's one of the sort of fancy newer distributed patterns. Basically, you have synchronous reads and asynchronous writes. Building that pattern, if you read Martin Fowler's blog, he talks about it. But he says one of the cons is it's complex to build. With this approach, where you're just controlling the message flows, it's not complex to build. It's just a configuration of how your messages go together. And then you can analyze the system in terms of services. So I can say, well, there's a post service that lets me post my tweets, and it takes in a post entry message. And then it's going to spit out save the entry into a data store message. And it's also going to spit out this info entry message to let other services know that I have a new entry. And the index service, it's going to accept its own messages, search, query, search, insert, but it's also going to listen for those info entry messages so that it can index any new tweets. So I can specify a service like this, and then I can assign that to teams or developers. And they can build versions of this service over a period of iterations. If I'm waiting for somebody to implement the index service, I can mock it up really, really simply, because I just simulate the message responses. I don't need to mock up a complex object hierarchy, which is one of the pains you have in unit testing when you want to mock things up. It's really painful because you have sub-objects and construction of objects and all that stuff. I don't have to do any of that stuff. All I mock up is message interactions, which are really easy to do. I can also define my service interactions. Whenever I do a search, I send a message from search to index, and that message is consumed. And if I send an info entry message, well, that's observed by the indexing service, and it's observed by the fanout service, which is going to send it to all the million users. In fact, if you're thinking in terms of the interactions, you can break them down into 4 categories. These messages are either synchronous or asynchronous, and they're either consumed or observed. So this kind of corresponds to work queues or pub sub or direct HTTP requests, that sort of thing. So if I look at my little Twitter clone, I have inbound requests from HTTP clients. I have a front service, which routes them to different places. It's a proxy, essentially. And I have a home page. I have a search page. I have my own page that lists my own tweets. And I have an API service that implements the API, the REST API for the system. And if I look at the interaction from the home service to the timeline service, so I have this timeline service that gives me my tweet timeline. I send a timeline list message, and it's going to give me back the list of tweets that I have to see. Same for search. The search page sends a search query message to the index service and gets back a list of results. On my own page, I just access the tweet database directly. The API service deals with posting an entry and following a user. So when I click on that follow button, that's a post request to say follow the user. A slightly more complex interaction model is around what happens when I post a tweet. Well, I need to store it somewhere, which is the entry store. And you can see I've composed entry store with entry cache. So entry cache doesn't have to exist. I'm just saving things into the store. But I can inject a cache in between those messages. So I don't have to change my code to get caching. I intercept messages to get caching. I also send out this info entry, which goes to the index service, which just listens for new tweets and indexes them as they come in. And the fanout service, it's not a synchronous interaction because that would take too long. So I post a tweet, And asynchronously, it says, there's a new tweet, and then that, over a period of minutes, will go out to my 1 million followers. So I'm just going to show, I think we have time for a tiny little demo. I'm just going to show that system in action. OK, so when you're running a whole bunch of microservices locally, you kind of need a little bit of tooling. The README for the Twitter clone kind of explains how to use this Fuge tool, which runs all these 14 microservices. But if I start them all up, they use this swim protocol to find each other. So they're just automatically finding each other. I haven't provided configuration. I haven't said which ports they live on or DNS names or any of that sort of stuff. So they're all up. And if I load up the foo page and I post, let's say, AAA, that's going to post my tweet. And then if I go and search for it in the bar user and follow, then you can see on the bar user's page the result came up. These are my tweets in my timeline. So let's just take another look at that from a messaging perspective. So I'm loading the timeline for the bar user. What does that actually look like? So this is a simplified log. So I'm on the home page for the bar user, and it sends a message that says, I'm user bar, list my timeline. That goes to the timeline shard service. So if I have millions of users, I have millions of timelines. I can't keep them all in one database. I need to shard that database. But if I'm following a database per microservice, how do I put that together? Well, I have separate microservices that deal with separate shards. So I'm splitting up my data in various ways. And then I have a sharding microservice that sits in front. So from the perspective of client microservices, I just do a timeline list. I don't know that there's sharding going on. There's a sharding microservice that does that. And I don't have to start with that. I don't have to make a decision at the start of my project to shard. Again, I've composed sharding into the system. I've made a decision down the road when I need to scale, oh, let's do sharding. I didn't have to do sharding at the start. In fact, if you look at the code base, there's an example with and without sharding. So anyway, the sharder decides that it's shard 0, and it goes to shard 0 and asks for the timeline list. And I also need to ask who my followers are, because I want to have a follow button for people that I'm not following yet. And the timeline list ultimately responds with that AAA tweet. And you can see it works its way back through the shard 0, back to the sharded timeline sharder, back to the home service. So you can see that there's a message flow. This logging also indicates something really, really important if you're trying to debug these systems. You can see that I have a correlation ID here. So I have an ID that traces its way all the way through the system. So we found it's useful to have two parts, a specific message ID and then an interaction ID. So in this case, WY is an interaction ID, and I can see all of the things that this interaction caused. You can see all of my identifiers here have WY at the end. But I can also see that home created this user bar timeline list message, and it had an ID of VQ, and then I can see that the timeline shard also got this VQ message. So I can chart, I can chart this up, and I can do nice diagrams and all that sort of stuff. If we look at the code for this interaction very, very quickly, this is the home service. It's a happy server, so just as a random recommendation, happy is better than express. We find it to be better. It's the stuff that Walmart uses. Most of this is just configuration, but here's the kind of important piece of code. So I've defined a root, which is /user, which is the user's homepage, and I'm sending timeline list. And when I get that back, I have a list of entries, and I just inject them into my HTML template. And then if I look at the timeline side of things, you can see that ultimately The list implementation is I just load it from my local database. So here I'm saying whenever I see the timeline list pattern, call that list implementation. But how do I hook the two things together? This is my business logic. I've said nothing in this business logic about how the systems find each other. That happens here. So I'm loading timeline logic as a set of patterns into this library. And then I'm saying I'm exposing timeline and shard as the pattern that I care about. So whenever I see a message that has any timeline value and a shard of 0, because I'm shard 0, for example, I'll get those messages and act on those messages. And then if I go up another level to the actual sharder, you can see that this is slightly simpler. I'm saying whenever I see a JSON document that has a key that is timeline with any value, I want it. So listing the timeline or inserting things into the timeline or whatever. And then I do a little bit of composition of my components, because I turn that JSON document, which doesn't have a shard identifier, into one that does, and I send it out again. So resolve shard just adds another key, shard equals 0 or shard equals 1 or whatever, and sends that out. But you can see here that I have not specified the location of anything. I haven't specified any ports or host names or any of that sort of stuff. Each microservice finds itself and finds the other services that it needs. Just to go back as a last example, when we do the search, so if I search for A, you can see I went from the search homepage to the index, and I called follow as well because I want to make sure that I put the follow buttons in. And you can see in this case that I'm calling, my process ID is 83729, and I only have one instance of search running. But I can start another instance of search. So you can see I now have 2 instances of search running, and the new one has joined the mesh. So if I do a search, okay, that one's using 83729. But if I do another search, you can see that the new one uses 83737. I can add as many searches as I like on different machines, and now I've got scaling. Or if I'm making changes to search, I can add a new version of search, still have the old versions running very, very simply. You can see that not only can you do this in production, but also locally. It's very, very easy to develop. So I have my whole system up and running. I'm working on the search functionality. All I do is focus on that search microservice, make my changes, restart it. Everything else is running continuously. So my development cycle is 50 milliseconds. I don't have to wait for the whole system to start up again. Okay. So that pretty much concludes my talk. It's a tiny little plug. I'm writing a book on all of these ideas called The Tao of Microservices, and it's in Manning on early access. So it kind of covers these ideas in more detail. And it uses Node mostly as the example language. And it is about building large-scale enterprise apps and how you use these ideas to avoid technical debt. Once again, it really isn't about callbacks versus promises or any of that sort of stuff. It's the large-scale structure that counts. It's the large-scale architecture that is the important thing. Thank you very much, guys.